So our next speaker is Sören Christensen, and the title is Equilibria in Markovian stopping games.
Yeah, thank you very much. And of course, also thank you to the organizers for this great workshop here. Today, I present joint work with Christopher Lindenschild from Stockholm University and Boy Schulz, PhD student of mine in Kiel. So yeah, it's very good fit that Ernesto gave the talk right before, because my talk is also about Dünken games. But I would like to discuss the role of randomization. In Ernesto's talk, there was no randomization. We just had first entrance time, so no player was randomizing anyhow. And if we extend the class of games, then it is clear that we need some kind of randomization in order to obtain equilibria. So I'd like to start with a very elementary introduction, just to fix some ideas which are important later on in the talk. And I start like as you were my students in year 2 or so, and the first time you learn something about game theory, yeah. So we start with this formulation of a 2-player normal form game. So Ernesto and I, we are playing. We can choose both a strategy S1 and S2, and we have reward functions both depending on the choices of both players, right? And we both want to, we are both maximizers. In all the talk, both players that we have are maximizing, right? So Ernesto and I, we would like both to maximize. But of course, what does maximization mean here, right? It depends on the choice of the other player. So the concept that already Ernesto has used in the previous talk is this of an equilibrium. So yeah, this means that we both do not want to deviate if the other player stays with its strategy. So, and in general, of course, we might have many equilibria. We cannot hope for uniqueness in many such games. We have many different equilibria with very different values, right? And but one question which can be answered positively is the one of existence, at least under some assumptions, right? And of course, you know, perhaps all these famous odds versus even game, both Ernesto and I, we show a number of fingers, and if we both show an even number, then I win, or an odd, if we both show odd number, I win, and otherwise Ernesto wins. Yeah, so this famous game. And if our strategies are of a pure type, then of course we cannot hope for an equilibrium, because if I tell and Ernesto and I go with the strategy both show odd, right? Ernesto would immediately change. So even in order to win, and other way around. So it's very clear that here you have no such equilibrium, first of all. So you have to extend, if you want to come up with equilibria and for the game to be fun, more or less, we need some kind of randomization. So we both want to hide our decision. And so instead of pure strategies from this set, odd and even, we randomize and both take a probability measure. And if we both flip a fair coin, what we show, then both our own fair coin, then we immediately see this is an equilibrium. So the first observation we should keep in mind is that even in very easy games, usually randomization is needed in order to have equilibrium. Okay. And the second thing, I do not have to tell you, but I still do this. If we have a Markovian type of stopping problem of this type, then there is this large class of stopping times containing very difficult mathematical objects. But if we have but if we are in a Markovian situation, all that we have to consider if we want are first exit times, okay? So I destroy everything here, okay? Our first exit times. So we can characterize everything in principle under some assumptions, of course, by this continuation set C, right? And this has 2 important consequences. The first one is that, okay, it fits very well to this Markovian framework above, and it allows us to use all the tools that we have seen in so many talks here in order to change from stochastic processes to functions and in some sense to solve the problems. And the second observation is one that Goran has, of course, mentioned in his talk, this issue of time consistency, and that it fits great here if we solve this stopping problem, this maximization problem here, and if we have such kind of this optimal time, and we wait some time and haven't stopped yet, right? We arrive here and ask ourselves in this sub-problem that we have now, what should we do? How should we act? If we take the canonical sub-problem of just restarting the process from there, this is still optimal. So this is very good, and of course it is Markovian, this time, in the sense that our stopping decision just depends on the state. Okay, so the second observation is for this Markovian stopping process, we would always look for Markovian stopping times. And now we come to Dynkin games. And if I speak about Dynkin games, here in this talk, I always have an underlying diffusion process, linear diffusion. You can think so. I will later on say something about boundaries, but at the moment, just think of any kind of diffusion. And now I'm not talking about zero-sum games, as it was in the previous talk. Both we have our own reward functionals. So if I stop first, then I get G1, as we both observe this process X. If I stop first, then I get G1. If Ernesto stops first, I get F1, and there are corresponding functions for Ernesto, G2, and F2. And in general, we do not say more. Of course, some structural, some regularity properties, but nothing more. But of course, this situation that Ernesto has considered is the one that G1 is equal to minus F2 and G2 is equal to minus F1. Then we are in a zero-sum situation. So we have a cash flow from me to Ernesto. Yeah? But of course, there are interesting stopping games also where this is not the case. And one big class of such games are the war of attrition games, which means in our case that this F1 is larger than G1, F2 is larger than G2. And if you want to have it's perhaps clear where this name comes from, right? Unfortunately, we have to talk about this kind of things nowadays again. So we think so that we are in some kind of war, hopefully not Ernesto and me. And perhaps we want to end the war, but we do not want to do this first, right? We want the other to give up first. So this is the situation. And here, for instance, it is very clear that usually we want to hide our decision. We do not tell the other exactly what to do, but we should, perhaps it's very, it seems obvious that in certain situations we should randomize, right? In order to get equilibrium. Okay, and I will go with these two. Of course, there are more like different kind of games, but I will go with these two special cases. And now comes this question of an equilibrium. And if we consider this stopping game just as a normal form game, as I've written down here for a fixed initial state X, then we can write down what an equilibrium is, just this. Yeah? But of course, there's this role with this X. And in Ernesto's talks, it was very nice because he solved the problem for all X. And his underlying strategies were exactly of this type that we've seen here also of a Markovian type. Yeah, so this is very nice. And this is the case for many problems which can be solved more or less explicitly in this setup. And this is the one type of results. Under some, I wrote restrictive, let's say more or less restrictive assumptions. Yeah, in some subproblems, we can find equilibria in first exit times. And then everything is great, right? With a very good interpretation in terms of subgames, because if both Ernesto and me, we haven't stopped yet. Yeah, and we changed our state from here to here. Then if we solve the subgame we are faced with, we can just go on with the strategy we have seen before. No problem about this. So in this situation, everything is fine. And here again, our strategies fit very well to the Markovian situation because we made our decision whether to stop or not just on the state we are in, the one which our payoff also depends on. And then there is another class of results, and this is for general payoff processes. So usually no Markov structure or something is assumed. And then, okay, as I've said before, we need to go to randomized strategies. And randomized strategies are here randomized stopping times. So there are many equivalent definition of what this is, but you can think so that we just randomly pick a stopping time, which is, of course, well, a very large class of objects we can pick from, right? Very, very huge class. And there are existence results of this type. Okay, there exists equilibria of this particular type. So in this normal form formulation for a fixed initial state, so everything, just one process given, then we can find equilibria to this normal form formulation. But we are then in this situation that in general, if we take such kind of a pair of strategies, we have path dependence. So this means that if we have such kind of an equilibrium, and we went on and haven't stopped yet, and consider the subgame, the usual subgame you're faced with then of this means the same Dünken game as we had before, but with another initial state y. And in general, there is no hope that our equilibrium is also an equilibrium there, because our decisions for both of us depended on the path we have seen so far. And what I would like to discuss here is a class of stopping times. This is just in between. Yeah, we have this class of first exit time, which is nice because of this Markov property, but it's too small to guarantee existence. And then we have this class of general randomized stopping times, which is much too large to gain anything from this information that we can find an equilibrium in there. Yeah, it's just super huge set. So we cannot hope to use this for finding equilibria explicitly. And we want to have something which respects the Markovian framework. And I'm, of course, I do not want to claim that I'm the first person who asked his or herself this question. But okay, still want to introduce this. And for those of you who are familiar with killing times of diffusion, this will not be super surprising what happens now. If I go for this Markovian kind of setup, in this diffusion case, I can characterize everything, of course, by a first exit property. So this first exit times are, of course, good Markovian stopping times. But in addition, I have measure lambda on the continuation set, which gives us the stopping rate of this underlying process. And formally, you do so that associated to this measure lambda, we consider a continuous additive functional. Here L is the local time. And here say lambda is, I don't know, density or what, yeah, something like this. So, and you consider the continuous additive functional, and you stop either when you leave this set C or when this continuous additive functional exceeds an independent exponential time. And due to this memoryless property, right, it is perhaps not super surprising that what comes out respects in some sense the Markov property, because here, I mean, this rate with which you stop just depends on the point you are in. Yeah. So this is this measure lambda on the state space. And if you want to make this precise, you can say so that, well, it respects these stopping times that we've seen before, respects the strong Markov property. One has to be a little careful with extending the shift operator because you have this extra source of randomness and so. But in principle, these are exactly this kind of stopping times. And yeah, they seem to be, to me, a good candidate for this purpose. Yeah, this is, of course, a larger set than first exit times, but it's given by this set and a measure. So in principle, everything is given by one measure. You have to specify this measure lambda. So you are, of course, very much in the middle. And we have this typical Markov property. So if you have here, oops, if you have here such kind of a time of an equilibrium in these kind of times where this property holds for all x, as we have seen in the previous example, then we have a good interpretation for subgame perfection. Then this holds that if Ernesto and I follow this strategy and haven't stopped so far and consider the subgame, then we can just follow the old strategy and still have an equilibrium. So the main question now is, okay, do there exist equilibria in these kind of times usually? And can they be constructed explicitly in certain examples? And I start with the construction in the zero-sum situation. And there you might say, oh, well, everything is known in the zero-sum situation. Okay, have to be careful here. Everything is known in this zero-sum situation. This is what Ernesto has just mentioned, this super nice geometric characterization or solution to these kind of problems using this semi-harmonic characterization, right? So if you have reward functions, now we have to be a little careful. Okay, I should explain this for a moment because I've a little changed notation here. We are now in the zero-sum situation, so it doesn't matter whether we study Ernesto's point of view or my one, and we just, for simplicity, take my point of view. So I'm the maximizer here, and if I stop first, I get F1. If Ernesto stops first, I get G. I get F. If Ernesto stops first, I get G. And it could also happen that we stop at the same time. Then I get H, and Ernesto just gets minus these quantities. And if we have this ordering that F is less or equal H, less or equal G, then everything is great, right? So here is G. Here's this function G, here's this function F, and you just pull a rope between these two obstacles and everything is known. So it's super, super nice. Whenever I tell students this, they like a lot, yeah? So this is very nice geometric characterization. But the question is, what happens if this ordering condition is not in place? What happens, for instance, if H is larger than G? Or if there are regions where this G is smaller than F. What is then? And the good message is that basically with these results we already have, everything is solved, but one has to be a little careful and think about why this is so. So in general, we might have very difficult situations. So very many different orderings of this F, H, and G are possible. And we just split the state space into intervals where one or the other ordering is in place. Yeah. And then we consider modified reward functions, F tilde and G tilde and H tilde. And we always choose them as one of the functions we had seen here already. But which function to take depends on which interval we are in. So one has to think a little how to do this. But the message is, if we have this difficult situation, by just concentrating, we can rewrite this into a situation where we have a game as before, as an auxiliary kind of problem. And thus, this can be solved as before. And actually, the value function which comes out here is the value function for our game with general ordering. But in general, there are no equilibria in first exit times anymore. But we can always find equilibria in randomized strategies. And just to give you an example how this can be done. I mean, if in this situation H is the largest, say, yeah, or the smallest. Let's say H is the smallest function. So if we stop at the same time, I have to give much money to Ernesto. What I do is, instead of stopping, if I would stop, Ernesto would also stop immediately, so that I have to pay much. But I stop with a super high rate. And if I stop with a super high rate, Ernesto has no chance to stop at the same time I stop. And there are other cases which can be treated similarly. And what comes out in the end is that you can always find global Markovian randomized epsilon Nash equilibria. And in some situations, just epsilon equilibria are possible. But in principle, this can be done the very same way. So this restriction on this ordering is not needed. But now I would like to come to this more general existence question. I mean, when you come to optimal stopping, you have this nice theorem that I presented at the beginning, right? So first exit, you just consider first exit times. Everything is fine. So this corresponds to here to existence of this Markovian. Do we have more general existence theorems, although we cannot construct this solution? And we are talking about existence of equilibria, then we're talking about fixed point theorems, right? If Ernesto and me are considering our best response mappings, if Ernesto has chosen some strategy, some stopping time, what is my best response? If we consider this kind of mapping, then equilibria are just fixed points of this mapping. So the question is, if we want to prove existence of equilibria, can we find a fixed point? And usually what is used there are these theorems of Kakutani type or generalizations of this. So what we need in classical Kakutani's theorems is that the underlying space should be compact somehow. We need some kind of continuity of this best response mapping and a notion and some variant of convexity. This is usually the ingredients you need, convexity of the image sets. So, and here our underlying space are these Markovian stopping times. And if we want to apply such kind of a fixed point theorem, we need to say something about topology. Right here, you say something about compactness, continuity. So we need some notion of convergence for our stopping times, Markovian randomized stopping times. The first thing you could think, okay, we have stopping times, you could just think about convergence of the random variables. This doesn't lead anywhere. So it doesn't just help for the purposes we have. The second could be, okay, we characterize everything by a measure here. Everything is given by measures. Couldn't we consider var convergence of measures? Our stopping times converge. If these measures converge, could be one idea. Or we could say, in the end, we are interested in distributions, right? We're interested in the time it takes and the point where we end in. Could it be that we could say that these stopping times converge if these guys here converge, this distribution converge for all initial points? Which one is the right one? Well, no one is the right one for all purposes immediately. The middle one has the problem that we cannot expect compactness. When we have general infinite measures here, we have no chance to expect compactness. Everything else is fine. With this distribution, we have compactness. And this is really a theorem. So when you think about this Markovian randomized stopping times, well, it really takes time to prove that with this topology we propose here, we have compactness. And this is something which you can take out for all problems that you always ever consider in this context. So we have compactness of this space. This is nice, but we have a problem with convexity. If we average two distributions of this kind of times, there will not come out a distribution of this kind of type. So, and what we did is we combined those two. We said that first we consider the discretized problem, where stopping is just allowed in a discrete set, in a finite set, subset of the state space. This we used. And there you can use classical Kakutani to come up with equilibria. And then we just made this grid finer and finer and used the compactness here in order to prove that the limiting object is in equilibrium in this original game. And so we see that in this war of attrition situation, where actually this war of attrition thing hasn't been used much, just for continuity, there always exists an equilibrium in this Markovian stopping times. And I should say here that some weeks after we've published this result, Jean-Paul Decamps and co-authors came to the same conclusion using little different methods. So this was a little, well, that we worked on the same kind of thing in parallel. So this is how work, well, it's good that they came to the same conclusion at least. And also the calculations are in some sense similar. Okay, so to conclude, I would propose to consider randomized Markovian stopping times when you are considering Markovian stopping games. Usually you should consider these. Sometimes you can directly construct equilibria, but sometimes you can just come up with existence results. But perhaps well, we now have all the tools which are needed in order to carry this out, also perhaps for other classes of games. And just one side remark for those interested. The last month I was interested in these diffusion generative models from machine learning. And interestingly, we're dealing a lot with age transforms, and so there, these randomized Markovian stopping times also come up there. But this is a talk on its own, I just wanted to mention. Thank you.